Hi, STAT students. Welcome to Section 8-2. We're going to put all our bits and pieces together, and we are going to do some hypothesis testing for a mean using the z-table. You can tell that simply because of the title. So let's just do a quick overview here first. So z-test for a mean. We're going to use z because we know sigma. Right, so same rules apply. Our sample size we're not sure about, but we definitely know that we know sigma. Sample size is probably greater than or equal to 30. Again, that's our second thing that we look at. I look first to see if we know our population standard deviation. Here's a big one. Here is the actual calculation you're going to do. You probably have seen that z is equal to x bar minus mu all over sigma over the square root of n. We've used that calculation for central limit theorem before. We know this formula, so the same thing applies. That is going to be a part of our hypothesis test. And we're going to use the z-table, so make sure you've got that out. Just to refresh your memory, over on the right-hand side here, we know that x bar is our sample mean. We know that mu is our population mean, so we're making a decision about mu based on our x bar. We know that sigma is our population standard deviation, and of course, n is our sample size. All right, so this is the big thing on this page right here. Make sure you highlight that or mark that down. We're going to use that calculation. So when we're using the p-value for hypothesis testing, the first thing we should probably do is talk about what p-value actually is. I try to always say p-value because I don't want you to get it confused with the probability of, but it still is very similar. So p-value stands for the probability level, which is actually our area under the curve of standard normal distribution. So we're going to look at that 4-digit decimal from our z-table, and then we're going to compare it to alpha to make a decision. Remember, alpha is our significance level, goes along with how confident we want to be. And since we're using mu and x bar, again, we're going to our z-table. If we were using mu and x bar, but we didn't know sigma, we didn't know our population standard deviation, that would make a difference, right? So we're going to use a z-table for right now, not for every case. So keep in mind, nothing is absolutely true or false. We use our sample data just to see if we've got enough evidence. And the only way to be 100% confident is using our population data. All right, so here we go. Let's talk about our steps. This is always a 5-step process. On the back of your notes, we've got steps 1 through 5. Nothing's going to change through the whole chapter. So whenever you read a problem, the first thing you are going to do is you are going to state your H sub O and your H sub 1 and identify the claim. We've done that already, right? H sub O is always a statement of equality. H sub 1 tells us if it's right-tailed, left-tailed, or two-tailed. The claim is important because of that table we filled in for our last step that says there is enough evidence to reject or to support, or there is not. Step 2, we're going to compute our test statistic. So in this case, in this section, our test statistic is calculated with z equals x bar minus mu all over sigma over the square root of n. So that's where we're going to do an actual calculation. We're going to get a value. In step 3, we find our p-value by going to the z-table. We just calculated a z-test statistic. Now we're going to the z-table. Step 4 is to make a decision. You have 2 options for your decision. You are either going to reject H sub O or do not reject H sub O. I also want to just mention, this is where we are going to compare p our p-value and alpha. So that's what tells us what decision to make. And step 5, summarize the results. And I'm going to insist that you use context. What is the claim that the SAT scores are higher than the national average? And I also want to remind you that we have the table that we filled out, and it's on the back of the notes. So again, we've done a lot of bits and pieces. The only thing that's brand new is step 4, making a decision. We haven't done that yet. Everything else we've done in some form or other. So I think I've got this out of order. So jump to the decision rule. We're going to come back to the example 8.5. So the decision rule, this is important. This is how we actually do step 4, which I just said is the only thing that's brand new. If your p-value is less than or equal to alpha, you're going to reject the null hypothesis. If our p-value is less than alpha, we are not going to reject the null hypothesis. So this is kind of an important thing to keep in mind. This is going to be the case for every single problem that we do. We're going to compare our p to our alpha in step 4. Remember, our alpha is our confidence. That's what was given to us. Significance level, 1 minus the confidence level. And the p is the actual area under the curve. It's going to be a 4-digit decimal, like 0.1058 or something like that. So we do need to mention, before we actually jump into this, we've got kind of 3 situations. So if our test is a left-tailed test, we are just going to use the area. We're just going to compare p to alpha. So the p is that area under the curve that we look up on our z-table. If it's right-tailed, we're going to compare, I'm not going to say compare, back that up. We have to, just like we did back in chapter 6 when we were talking about z-values, we have to do 1 minus the area. Oh my goodness, 1 minus the area. Because it's right-tailed and everything that's given to us on the z-table is to the left. We'll go back, we can go back and talk about that, and we'll draw pictures while we do these. If it's two-tailed, don't forget to compare p and half of alpha. Alpha over 2, right? Because it's two-tailed and we're splitting that alpha between the 2 sides. I know that's a lot. Again, more bits and pieces, but let's actually do a problem so we can compare it. So I want to do the first problem I want to do is right-tailed, just so to refresh your memory about what that 1 minus the area is. Oh, and I forgot, we're going to go back to this quick decision-making situation. So suppose teacher gives you a p-value of 0.0356. So basically, I did step 2, calculate the test statistic. I did step 3, I went to the z-table to get my p-value. Now I'm on step 4. So notice my H sub O is mu equals 50. And my null hypothesis, my alternative hypothesis, is mu is greater than 50. So I'm up here, it's a one-tailed test. This x bar equals 52 doesn't matter. That was just needed to calculate step 2, so you can just disregard that. So in example A, my alpha is 0.05. So alpha equals 0.05. If I'm going to compare my p to my alpha, so 0.05 compared to, I'm going to move there we go, a 0.0356, my p-value is definitely less than alpha, right? If you're a picture person, this whole shaded area over here on the right is 0.05 for my alpha. If I drew a p-value of 0.0356, that whole area of p falls inside that shaded rejection region. So we are going to reject H sub O for our decision. If P is less than alpha, reject H sub O. So for you visual people, all of the p-value fits inside the alpha. It doesn't overflow into the non-rejection region. What if I change my alpha? Take these guys right off of here. What if I change my alpha, for example, B, to 0.01? Now, when I draw my p-value of 0.0356, I'll jot this down. P is 0.0356. Alpha is 0.01, so I want to be 99% confident. This p-value of 0.0356, that overflows, right? It's bigger than the alpha area that's shaded. It goes into the non-rejection region. So my P is greater than alpha, so I do not reject H sub O. So if you just like the formula, if P is greater than alpha, do not reject. If P is less than alpha, reject it. If you're a picture person, you need to understand what you're looking at. Think about how your p-value, is it all contained within alpha or does it overflow? Okay, so now that I did that out of order, let's talk about an example of tuition fees. A researcher wants to test the claim that the average tuition fees at a public college are greater than $5,700. To test the claim, the researcher selects a sample of 36 colleges and finds the mean to be $5,950. Population standard deviation is $659. Is there enough evidence to support the claim that alpha equals 0.05? So let's do our first hypothesis test. I like to jot everything down. So let's see, test the claim that the average tuition is greater than $5,700, right? So that is going to be our mu. Because then that researcher went to a random sample of 36 colleges and found the mean of that random sample to be 5,950. And we know that our population sigma, standard deviation, is 659. We know that our alpha is 0.05. So I like to have everything over on the side. So I typed out the steps to start off with. So state our null and alternative hypotheses. So H sub O, you're always going to write down which one's which, just don't make an assumption. Notice H sub O always has our parameter, our population parameter in it, and we've got it. It's pre-written for us. Mu is $5,700. And what does the researcher want to test? That the fees are greater than that 5,700. So that means we've got ourselves a right-tailed test. So if I am going to draw a picture and mu equals 5,700, the researcher believes that it's greater. So which one's the claim? Greater than. And I'm going to just mention, put this in here, my alpha is equal to 0.05. So everything that they just gave us is jotted down, is calculated, is drawn. So step 2, now we need to calculate our test statistic. So our test statistic, Z is equal to X bar minus mu. That's all divided by sigma over the square root of n. So I've got myself a 5,950 minus 5,700. The value from your hypotheses always goes second, in case you like to have a definite pattern. over my standard deviation, 659, over the square root of my sample size. I'm going to go ahead and calculate that at a 2.28. Check my calculation, 2.28. Okay, so we've done that. We know how to do this. Step 3, we've done before, but we've never really done it this way. So find the p-value. So I notate it this way so I remember what I'm doing. I say I'm going to the z-table, and notice how I've got 2 decimal places in that z calculation. I'm going to go to 2.28 on the positive side. Go down to 2.2, across to 0.08, and I'm going to find the area, and that tells me it's a 9887. Remember, when we get an area from the z-table, it's a 4-digit decimal. If you refer back to what we said earlier under that decision rule, if it's right-tailed, if I think about this picture, I got a 9887, which means all of this, right, is 0.9887. Well, that's not helping me. So I have to use the same rules that I used previously, and I have to do a 1 minus. So right-tailed, subtract the area from 1. So if I do 1 minus 0.9887, I get a 0.0113. This is my p-value. So in that last example, I said, oh, it was pre-calculated. The teacher did step 2 and 3 for you. That's where that 0356 came from. So that means now, if you're a picture person, I'm going to go up to my picture. I'm going to draw in a 0.0113, knowing that my alpha is 0.05. So an 0113 fits in here. P equals, you can't see when I write in yellow, but P equals 0.0113. That all fits inside a 0.05. If you don't need the picture, and I just think about my P is 0.0113, my alpha is 0.05, my P is definitely less than alpha, which means it all fits inside, and it all fits inside the rejection region, and we're going to reject H sub O. Please write H sub O with your reject. So then I go to the table for the summarize, and I look to see, and I notice, oh, H sub 1 was my claim, and I rejected H sub O. So I go to that little 4-box table, and I notice that this is what I'm supposed to say. There is enough evidence to support the claim, and then I have to fill in the context. To support the claim that tuition is greater than $5,700. That tuition is greater. This is where your ELA skills are really going to come in handy. 5,700. That's supposed to be a 5. And we have just completed our first hypothesis test. This is so exciting, and we are good. I think let's hustle through the last one because it's a 2-tailed. So a researcher claims that yearly consumption of soft drinks per person is different than 52 gallons. Clue. In a sample of 20 randomly selected people, the mean of their yearly consumption was 53.7 gallons. The population standard deviation is 3.5 gallons. On the basis of the p-value, is the researcher's claim valid at 98% confidence, which means that my alpha is 0.02, right? 1 minus 0.98. So let's jot down our hypotheses and identify the claim. So I already have mu equals 52. And it just says that it is different So that tells me it's going to be a two-tailed. It also tells me that that's the claim, right? The researcher claims that it is different. So mu is not equal to 52, which is our claim. If we were a picture drawing type of people, we would have mu of 52. We would have two-tailed. And what would we have to remember to do with our alpha? We'd have to remember to divide that by 2 because it's two-tailed. So if our alpha is 0.02, that means the alpha over 2 is 0.01. All right, I'm all set here. So compute my test statistics. So I'm going to do my z, x bar minus mu. And that's all over sigma over the square root of n. Check my calculations on this. I ended up with a 2.17. So I'm going to go to my z table. I'm going to go to the positive side. So I'm going to go to z and find 2.17. And I'm going to get a p-value of 0.9850. So even though this is a two-tailed, I've got an area greater than 50%, greater than 0.5000, because it happened to be on the right side of the mean. So I have to subtract that again. I'm always looking for small numbers. Imagine trying to compare an alpha over 2 of 0.01 with a 0.9850. Just doesn't even make sense, right? So when I subtract that, I end up with a 0.0150, I believe. So my p-value for either end, that's the thing about the alpha, we split that, but the p-value for either end is a 0.0150. It just happens to fall on the right-hand side. So when I go to make my decision and I'm thinking about a 0.0150 compared to a 0.01, that's going to be a little bit bigger, right? So if I'm comparing my p to my alpha, should say alpha over 2, 0.01 compared to a 0.0150, this p-value is greater than my alpha. It overflows into the non-reject. So this is a do not reject. Don't forget to say what you're not rejecting, your null hypothesis. And if I'm going to summarize, my claim is H sub 1, but I didn't reject the equality, null hypothesis. So I say there is not enough evidence. And again, I'm going to the table. I don't have this memorized. There is not enough evidence to support the claim that, insert context here, soft drinks per person is greater or is different than 52 gallons per person is different than 52. That's a lot of pop, isn't it? And we've got our summarization with our context. So first two hypothesis tests, one reject, one do not reject, has nothing to do with what the claim is or whether it's one or two-tailed. It has to do with your p-value, steps 2 and 3, calculating and going to your z-table. That is it for section 8.2. We'll do a lot of practicing. Thanks for hanging in there. See ya.